In passing, we'll mention the circuit where the source is connected to the capacitor, and when we crank the source, what we're actually doing is removing electrons from one plate of the capacitor and placing them on the other. So we take electrons through the circuit like so. Okay, the electrons removed from here and are replaced here. And this side therefore becomes positively charged from the absence of electrons. This side becomes negatively charged from the presence of electrons. We'll see later exactly what happens in that situation. Well, maybe not exactly, but we'll do a pretty good job of approximating. Okay, if you have a wire with one cross-sectional area A1 here and a cross-sectional area A2 here, then we want to look at what happens, what the kinetic energy difference is between here and here. Again, assuming the same electron density, the same number of electrons per cubic centimeter here as here. Then the velocity in wire 2 is then by something very much like the continuity equation, practically identical to the continuity equation, is A1 over A2 times V1, the area ratio, the reciprocal area ratio times V1. So that when area A2 is less than area A1, V2 will be greater than V1. That's what I mean by a reciprocal. There's an inverse proportionality between velocity and area. Now this implies that the kinetic energy in wire 2 will be A1 over A2 squared times the kinetic energy in wire 1. And that's a KE sub 1, not a comma, not a KE sub comma. A1 over A2 is the ratio between the velocity here and the velocity here. So the velocity here is A1 over A2 times as great as it is here, which means that V squared is A1 over A2 squared times as great here as here. And it should be clear that that's what gives you this proportionality in kinetic energy, since kinetic energy is proportional to the square of the velocity. We're talking about electrons, so the masses are the same. Now, in that case, we have R1 over R2 to the fourth then times the kinetic energy, because, of course, the area ratio, if these are round wires, will be equal to the square of the ratio of the radii. Okay, so if this wire has radius R1 or R2 and this one has radius R1, then the ratio of kinetic energies turns out to be the fourth power of the ratio of the radii. Okay, now, if we have a circuit with a thin wire here and a thinner wire here, why is it that this wire is going to glow more brightly than this one, or will it? And we'll see in a minute.